Hello everyone. This week we will discuss the naming of organic compounds. Let's begin by becoming familiar with the simplest group of organic compounds, the hydrocarbons. Hydrocarbons are so named because they are compounds made up of only hydrogen and carbon atoms. There are three types of hydrocarbons: the alkanes, alkenes, and alkynes. Hydrocarbons are named using prefixes to indicate the number of carbons in the molecule. Alkanes are the simplest hydrocarbons. The first 10 alkanes are given in this table. Methane has only one carbon atom. Ethane has 2. Propane has 3, and so on. If you are already familiar with Greek prefixes, then pentane to decane should be easy to remember for you. It is important that you remember these prefixes for the number of carbons because many organic compound names are based on them. The molecular formula given here is a condensed version wherein the inner carbon-hydrogen bonding are enclosed in parentheses with a numerical subscript to indicate how many such bondings exist in each of these alkanes. So for example, heptane has 7 carbons. Counting the first and last gives us 2 carbons, and multiplying the subscript 5 with the C in parentheses gives us 5 more carbons for a total of 7 carbons. The suffix in the name tells us what group of hydrocarbons we are referring to. In the previous module, you were introduced to alkenes and alkynes as functional groups. An alkene is a hydrocarbon with a double bond between carbon atoms, whereas an alkyne has a triple bond between carbons. The suffix of a hydrocarbon name tells us whether or not double or triple bonds are present in a hydrocarbon. Here are examples of alkanes, alkenes, and alkynes. Octane has 8 carbons. Butene has 4 carbons and is an alkene because it has a double bond. Pentyne is an alkyne with 5 carbons and a triple bond. Remember our condensed molecular formula? The CH3 refers to these two sections at the beginning and end of the molecule, and the CH2 refers to the inner carbon-hydrogen bonds. So for octane, there are 6 inner CH2 bonds. Hydrocarbons can be represented using the Lewis structure, but it can be difficult to write all CH bonds when dealing with long hydrocarbon chains. So the condensed structure and the line structure are used to shorten their molecular structures. Hydrocarbons can be visually represented using Lewis structures, condensed structures, and line structures. You should become familiar with recognizing organic compounds using line structures because you will use them extensively throughout the remaining modules. The important thing to remember with line structures is that each corner or bend represents a carbon atom, and the line represents the bond between the carbon. Hydrogens are not represented, but they are understood to be present. You need to pay careful attention to the lines or bonds as they will tell you how many hydrogens should be attached to the carbon atom. Remember the octet rule? When drawing line structures, always make sure that carbon follows the octet rule. If there are double lines, how many hydrogens should be attached to carbon? Alkanes can exist as independent molecules, but they can also be part of a larger compound as a side chain or substituent. When this happens, alkanes become a functional group and takes on a different suffix. Instead of ending in "ane", the names end in "il". But not all alkanes become alkyls. Only the first 4 alkanes, do so. When methane becomes a functional group or a side chain, its name changes to methyl. Ethane becomes ethyl, propane becomes propyl, and butane becomes butyl. We will know more about alkyl groups as we move on to naming complex organic compounds. Here are the chemical structures of the alkyl groups. Notice that when an alkane becomes an alkyl, it loses one hydrogen atom. This happens when the alkyl group bonds with a bigger molecule. As we just learned, naming simple hydrocarbons is straightforward. Just count the number of carbon atoms and remember the corresponding prefix and suffix. But how do you name organic compounds with a functional group such as an alkyl group? How do we name propane when there is a methyl group attached to it? The IUPAC system of nomenclature can help us do that. IUPAC stands for the International Union of Pure and Applied Chemistry. It is a systematic way of naming organic compounds that has two major parts: a stem name or parent chain name made up of the longest continuous chain of carbon atoms in the molecule, and substituents or side chains attached to the parent chain. These side chains are named and numbered according to their positions on the parent chain. Let's name this compound using the stepwise procedure of the IUPAC system. The figure on the right is its line structure. I've added it here so that you can become familiar with how this compound is drawn using line structures. So first, we need to find the longest continuous chain of carbon atoms in the molecule, or the LCC. We can start from the left or from the right. The easiest way to find the LCC is to start with a straight chain of carbons. So if we count this as 1, 2, 3, 4, 5, 6, that only gives us 6. But we can go up here to make it 7. If we count this one here, 1, 2, 3, 4, and go up here, that gives us 5 carbons. Okay, what about this one here? If we go 1, 2, 3, 4, 5, 6, 7, that gives us 7. So we have 2 possible LCCs. Either one of them is correct because, as you will see later, they have the same substituents. So a 7-carbon alkane is called heptane. So our parent chain is heptane. So let's say we picked this carbon chain as our LCC. Now we have to number the carbon atoms in this chain. According to the rules, numbers are assigned in the direction that gives the lowest numbers to the carbon atoms with attached substituents. So in our case, we have a substituent assigned to this carbon, and another assigned to this carbon, and another one assigned to this carbon. If we start our counting from right to left, this would give us 1, 2, and this would be 3. If we start from left to right, we would number this as 1, 2, 3, 4. So in this case, the second carbon here has a substituent and it has a lower number than this carbon here, which is number 3. So we number from left to right. So this is carbon 1, carbon 2, carbon 3, 4, 5, 6, and carbon 7. Now it's time to name the substituents or the side chains. Remember that our parent chain is this heptane. We have three substituents. This one here, this one, and this one. This substituent is methyl. This one is also methyl, and this one is ethyl. Now, when writing substituents, we arrange them in alphabetical order. So, ethyl should come before methyl. And then, we have to include the carbon number of the parent chain to which the substituent is attached. So, ethyl is attached to carbon number 5. Because remember, our numbering is from left to right. Now the two methyls are attached to carbon number 2 and number 4. Because there are two of them, we use a prefix to indicate this number. In this case, we use di. If there are 3 methyls, we use the prefix tri. If there are 4, we use the prefix tetra. So we have 5-ethyl, 2,4-dimethyl as our substituents. As we learned in the previous slide, there are a couple of things to consider when naming substituents or side chains. First, if the same alkyl group appears more than once, the numbers of all the carbon atoms to which it is attached are written as part of the name. Next, if the same group appears more than once on the same carbon atom, the number of that carbon atom is repeated as many times as the group appears. The number of identical groups is indicated by the Greek prefixes di, tri, and tetra. These prefixes are not considered in determining the alphabetical order of the substituents. Now we need to combine the name of our substituent groups to our parent chain name. Think of the parent chain as the surname of this compound. It is written last. The name of the substituent is written first. So our parent chain name is heptane. Our substituent name is 5-ethyl 2,4-dimethyl. So we write this as one long word. The name of this compound is 5-ethyl 2,4-dimethyl heptane. Let's have another example. This molecule has a double bond, which makes it an alkene. First, we find the LCC. When a double bond or triple bond is present in a compound, we can be sure that it is part of the parent chain, and we start counting from the end closest to the double or triple bond. So in this case, we number this carbon as 1, this one as 2, this one as 3. If we go up, we have 4 carbons. If we go further to the left, we have 4 carbons. But if we go down, we have 5 carbons. So our LCC has 5 carbons. If you remember, a 5-carbon alkane is called pentane. But since this is an alkene, we call this a pentene. And we attach the carbon number where the double bond is. So our parent chain is 1-pentene. Next, we have to identify the substituent groups. We have one methyl substituent here and another methyl substituent here. So both of them are attached to carbon number 3. So in this case, we write the number 3 twice to indicate that there are 2 methyls, And remember, we use the prefix di to indicate two methyl groups. So the side chain or substituent group name is 3,3-dimethyl. And then if we combine it to the parent chain name, the name of our compound is 3,3-dimethyl-1-pentene. And that's it for this week's lecture. In this lecture, we identified prefixes and suffixes used in the naming of simple hydrocarbons. We learned about different structures used to represent organic compounds, and we practiced the stepwise procedure in naming organic compounds using the IUPAC nomenclature system. And that ends Module 9. Modules 9 and 10 will have a combined activity worksheet. Please refer to Module 10 for the activity. Thank you for listening.